Hello everyone, welcome to the last video of the course, Detecting Pedestrians with Support Vector Machines. In this section, we will direct our attention to another well-established supervised learner in the machine learning world, Support Vector Machines, or SVMs. We will apply SVMs to a popular problem in computer vision, pedestrian detection. We will obtain a real-world dataset, perform feature extraction using the histogram of oriented gradients, HOG, and apply an SVM to it. Now we move on to the first video of this section, that is, Understanding Linear Support Vector Machines. In this video, we will begin with implementing and building the first support vector machine. Then we will learn to visualize the decision boundary. An SVM tries to achieve low classification errors too, but it does so only implicitly. An SVM's explicit objective is to maximize the margins between data points of one class versus the other. This is the reason SVMs are sometimes also called maximum margin classifiers. Let's implement our first support vector machine. For our very first SVM, we should probably focus on a simple dataset, perhaps a binary classification task. A cool trick about scikit-learn's dataset module that I haven't told you about is that you can generate random datasets of controlled size and complexity. A few notable ones are classification. This function generates a random n-class classification problem. Next function is regression. It generates a random regression problem. The blobs function generates a number of Gaussian blobs that we can use for clustering. So we will start by importing Datasets module, and then we will add and execute these lines of code. Here we have used makeClassification to build a custom dataset for a binary classification task. With this argument, we specify that binary classification problem has exactly two distinct target labels. For the sake of simplicity, let's limit ourselves to only two feature values, for example, an x and a y value. Also, we will create 100 data samples. Let's execute it. Post that, we will check the result by calculating the shape of x and y. Here, we expect x to have 100 rows as data samples and 2 columns as features, where the vector y should have a single column that contains all the target labels. On executing the code, we are able to achieve the desired output. Now let's visualize the dataset. We will plot the data points in a scatter plot using matplotlib with this block of code. Here, the idea is to plot the x values which is found in the first column of x against the y values that is found in the second column of x. A neat trick is to pass the target labels as color values, as we have specified in this argument. This is the figure which is generated on executing the code. You can see that, for the most part, data points of the two classes are clearly separated. However, there are a few regions, particularly near the left and bottom of the plot, where the data points of both classes intermingle. These will be hard to classify correctly, as we will see in just a second. The next step is to split the data points into training and test sets, as we have done before. But before we do that, we have to prepare the data for OpenCV. So let's start by importing NumPy module as NP. Then we will enter the code where we will specify all feature values in x as 32-bit floating point numbers, and target labels as either -1 or 1. Post that, we will execute it. Now we will import model selection as ms, and then pass the data to scikit-learn's train-test-split function. Here, as you can see, we chose to reserve 20% of all data points for the test set, but you can adjust this number according to your liking. Next, we will build the support vector machine. In OpenCV, SVMs are built, trained, and scored the same exact way as every other learning algorithm we have encountered so far. For that, first we will import the OpenCV module. Then we will call the create method to construct a new SVM. There are different modes in which we can operate an SVM. An SVM that tries to partition the data with a straight line can be achieved with this setKernel method. After that, we will call the classifier's train method to find the optional decision boundary. As you can see, the output we have got is true. Then, by executing this single line of code, we will call the classifier's predict method to predict the target labels of all data samples in the test set. Then execute it. Lastly, to get the accuracy score, we will use scikit-learn's metrics module. First, we need to import the module, and then execute this line of code to achieve the desired output. Congratulations, we got 80% correctly classified test samples. Of course, so far we have no idea what happened under the hood. Getting a system to work is one thing, and understanding it is another. Let us get to that. Let's proceed with visualizing the decision boundary. The idea is to generate a fine grid of x and y coordinates and run that through the SVM's predict method. This will allow us to know, for every x, y point, what target label the classifier would have predicted. So let's begin by adding this code snippet. Now we will understand this code step by step. Here, with this line of code, we define plot decision boundary function. The function takes as inputs an SVM object, the feature values of the test set, and the target labels of the test set. Then with this, we specify the step size in mesh, basically the sampling step. In our case, it's h. After that, to generate the grid that is also called mesh grid, we first have to figure out how much space the data samples in the test set take up in the xy plane. So, to find the leftmost point on the plane, we look for the smallest x value in x-test, and to find the rightmost plane, we look for the largest x value in x-test. We don't want any data points to fall on the border, so we add some margin of +1 or -1. As you can see, in our case, it is +1. We will do the same for y as well. From these boundary values, we will create a fine mesh grid with these two lines of code. Here, we make use of NumPy's arrange, such as start, stop, step function that creates linearly spaced values between start and stop, all step apart. We want to treat each of these x, x, y, y coordinates as hypothetical data points. So we stack them column-wise into an n by 2 matrix. Don't forget to convert the values to 32-bit floating point numbers again. Otherwise, OpenCV will complain. Here we have passed the x-hypo matrix to the predict method. The resulting target label ZZ is used to create a color map of the feature landscape. This creates a contour plot, on top of which we will plot the individual data points colored by their true target labels. Finally, let's execute the code snippet. The data plot will be generated using decision boundary function. The result looks like this, as we can successfully visualize a linear decision boundary in the generated plot. The SVM found a straight line, a linear decision boundary, that best separates the blue and the red data samples. It didn't get all the data points right, as there are 3 blue dots in the red zone and 1 red dot in the blue zone. So what can we do to improve our classification performance? One solution is to move away from straight lines and onto more complicated decision boundaries. Amazing! In this video, we learned to implement and build SVM using decision boundaries.